Students, today what we're going to do is look at an NMR spectrum and then be able to get a structure from the different resonances in the spectrum. So we're going to look at every resonance in detail, see what information we can get out of them, look to see if we can get the respective groups in the structure identified, and then try to put these different groups of fragments together to make a plausible structure that you think this would represent. So let's have a look at this particular spectrum, and I'm going to start at the very d-shielded resonances first, because you know that around 7.0 to about 8.0 we get aromatic proton resonances. So for this particular resonance we can identify an aromatic ring. We have 5 protons attached to that, which means that one of the positions must be substituted by something else. I quickly want to go from there to the molecular formula and subtract what I've done from the molecular formula, because this is quite a sizable chunk from the molecular formula. And if I look at this, I have a C6H5 fragment that I've actually taken from the molecular formula of the compound. If I subtract subtract this fragment from the molecular formula of the compound, I get C3H7. So these particular fragments here must add up to 3 carbons and 7 hydrogens. And if I look at the integration of each of these peaks, we can see that this very nicely adds up to C3H7. 1, 2, 3, 3 carbons, 2, 4, 7 hydrogens. So I've got all the fragments that I have sorted out. I just need to put these fragments together now to make sense. Now, you don't really need to look at anything more to put these fragments together to make sense, but I'll just go through the motions with you to show you that we can use these splitting patterns to put these fragments together. You'll see that the CH3 group at around 1 or so, and they've expanded it for you nicely here to see that it's a nice triplet. In order to be a triplet, the CH3 has to be next to a CH2 group, because then the CH3 would be a triplet. So this triplet here is due to this CH3 because it is next to a CH2. Now you only got a 3 carbon fragment left, so the other CH2 has to go here. And this CH2 that you find, this terminal CH2 that we find here, is due to another triplet that you see at around 2.5 here. They've expanded it for you nicely here, 2.5, this sort of triplet. And that's because it's next to the CH2 in the center. So you'll find that this CH2 in the center splits that methyl group into a triplet that you see here, and it splits the CH2 into a triplet which you see here. And in the process, this middle CH2 that splits each of the other resonances into triplets is now split into a multiplet, and you see the multiplet here. Now you might say 1, 2, 3, 4, 5, 6 is a sestet, and that's 3 plus 2 is 5 plus 1. That's not entirely true. Remember that CH3 and those CH2s, these protons are not equivalent. So we can't apply the n+1 rule here. It probably just works out like that because the different resonances coalesce together. Remember that in an open chain like this with a free rotation, the coupling constants between the protons is about 7 Hertz. So they might just coalesce to be like this. So this wouldn't actually be a sestet. I would actually call it a multiplet more correctly. So I have this particular fragment and this particular fragment to put together, and I can easily put that 2 fragments together to make a plausible structure. I can join the two up. So my one fragment is here, and I join the CH2, CH2, CH3 fragment to that. You need to note that the CH3 is in the chemical shift of the methyl region. The middle CH2 is sort of in the chemical shift for the methylene region. It's slightly de-shielded because of this aromatic ring, which is about 2 bonds away, but this CH2 directly bonded to the aromatic ring is much more de-shielded than it should be, and that's because of the pi system of the aromatic ring. So that's your structure for this particular spectrum. My next example that I have might seem slightly confusing, because if I look at the integration, there's just 5 protons in this spectrum, and if I look at this molecular formula, it has 10 protons. I'll come back to that in a second. I just want to run back quickly to this splitting pattern here. You see at 1, there's one here. I have a triplet at 2.4 or so. I have a quartet, a triplet in the methyl region of the spectrum. So that peak is probably a methyl group. It's in the methyl region, integrates to 3 protons, and I can join that methyl group now to something here, because there's only 2 resonances in the spectrum. So in this 2 proton peak must be a CH2. If I look at the splitting patterns of each of these, this CH2 is split into a quartet, and you can see here 2.2, and they've expanded it here to see it's very clearly a quartet. So this is a quartet, and the CH3, as you've indicated, is a triplet. 2 plus 1 is 3, so that's a triplet. 3 plus 1 is 4, so that's a quartet. So I have my 2 groups in there. This is not in the typical region of a CH2. Remember, a typical region would be somewhere around here, 1.2 or so. So something is de-shielding it here. If I look at my molecular formula H10 and C5, it means that these here must have doubled up. Remember, these integrals are relative, so it could be 6:4. So it could be 2 methyl groups and 2 CH2 groups as well. It could mean 4 methyl groups and 4 CH2 groups. These are just relative numbers. If I double up on my CH3s and CH2s, it would mean that I have a CH2 and a CH3 as well on the other side. And because they're equivalent, they must be symmetrical, or the molecule must be symmetrical, which means I have something down the center here to make them symmetrical. I'm going to count all these up, and this adds up to C4H10. And if I look at the molecular formula that I'm given, C5H10O, and I see what I have left. I have a carbon left, and I have an oxygen left that I need to fit into this structure on the top here. And what better way to do it than to insert a carbonyl group which satisfies the valency of carbon. I have 4 bonds around all my carbon atoms, and I come up with a structure for C5H10O. If I look again around 2.4, something de-shielded these 2 CH2s, and that has to be the carbonyl group. Remember that a protonated resonance next to a carbonyl group is roughly in the region of 2.2 to 2.3 or so. The next example has a molecular formula of C9H10O2. I have resonances in my aromatic region, so again I have an aromatic ring, 5 protons, so again there must be something attached to that aromatic ring, and then just 2 resonances here. One is in the methyl region of the spectrum, also integrates to 3 protons, is a triplet, we can see from there. The other is a CH2 from the integration. It's a CH2. We can't use chemical shift here because this is de-shielded by something. So integration tells us it's a CH2. It's a quartet, which means it must be next to a CH3. So in order to get a quartet, something must be next to a CH3. To be a triplet, something must be next to a CH2, which means these two must be next to each other. So the CH2 and the CH3 must be next to each other. Now something is de-shielding this carbon, and if it was just this aromatic ring, we saw earlier that the chemical shift is around 2.8, 2.9, or even around 3 sometimes. But this has shifted way down to 4.2. Much like when a heteroatom is joined to a protonated group, such as oxygen, or chlorine, or bromine. If I look at my molecular formula, I have oxygen atoms in there. But let's go about this systematically. I've got a C9H10O2 molecular formula. If I add these up, I've got C6, 7, 8, H5, 6, 7, 8, 9, 10, and that's all. If I subtract what I have from the fragments, from what molecular formula of the molecule, I get C, no hydrogens, and 2 oxygens. So I now need to join this aromatic ring together with this ethyl group here and somehow incorporate a carbon and an oxygen. So to incorporate a carbon and 2 oxygens, I would probably need to have this ester type of group that satisfies the valencies for all carbons and oxygens. And I now need to put that fragment, and that fragment together. And recall I said that this CH2 is de-shielded because probably of a heteroatom such as oxygen. And I see here I have an oxygen atom. So the ethyl group would probably go there, and this will be joined onto your aromatic ring. Alright, so the structure for this molecule would probably be the aromatic ring joined to the carbonyl, joined to the oxygen, joined to the CH2, CH3. And you can see from here I have 5 aromatic protons. So the CH2 would be a quartet, it is. The CH3 would be a triplet, it is. The CH2 would be de-shielded because of the oxygen of 4.2, and it is. So this is the structure for this particular compound. What if I said, okay, I have these groups to join, let me try and join them in a different way. There's one other way I can actually join these together to make sense, but that won't satisfy the criteria of the spectra, and I'll show you why. I could put the oxygen there, the carbonyl group there, and then the ethyl group to that. That would make good chemical sense, but this is wrong for the reason that this CH2 group, if it were joined to the carbonyl group, would be in this region. So the quartet would be here if I had this type of molecule. I'd expect a quartet to be somewhere around here. But the fact that the quartet is much more de-shielded indicates that the CH2 is joined directly to the oxygen atom. So you can't just have your fragments and put them together. Once you get the structure, you need to go back, see if it makes sense. And this example is very good for you to see that this structure makes more chemical sense because of the chemical shift of this CH2 peak.